Welcome to the final week 1 video. Today we will finally launch into real analysis proper. Everything up to now is a bit of a warm-up. What we will discuss in this lecture is covered in your textbook between pages 13 and 19. Your textbook actually covers a bit more than what we will in those pages. We will only talk about the good bits. The topic of this lecture is the Archimedean property. To get started, we have to review the order structure of the real numbers. By order structure, I simply mean the fact that we can compare two real numbers and decide if one is bigger than the other. In fact, given any two real numbers, we know that they are either equal or one is larger than the other. What we will do first is to codify systematically this ordering. The reason that we touch on this is based on the reductive type of mathematical reasoning. We want to know, what is the minimum assumption that makes real analysis work? Real numbers are in many ways very messy objects. Instead of trying to understand the real numbers in the full glorious details, we will identify the properties of the real numbers that have direct bearing on doing analysis or calculus. And later on in the course, instead of trying to use this nebulous concept that is real numbers, we will rely only on a few codified properties of the real numbers as pertaining to this order structure. In particular, we will know that even if we swap out the real numbers with something completely different, as long as we can still do arithmetic with this new set of numbers, and as long as it behaves like the real numbers when it comes to the ordering properties, then we can do calculus with this new set of numbers just as well as we can do with the real numbers. Here are the basic defining properties of how we compare two numbers. For conventional reasons, it is more convenient to talk about the less than or equal to relation rather than the strictly less than relation. First, any two numbers can be compared. That one can be definitely said to be bigger than or equal to the other. This property is called the connexity of the ordering. Second, if two numbers are such that either is less than or equal to the other, then the two numbers are equal. This is called the antisymmetry of the ordering. The third point is less of a property, but more of a definition. The fourth point is called the transitivity. It says that the ordering is unidirectional and cannot go around in circles. If A is less than B and B is less than C, then A is also less than C. For the most part, in this class, I will expect you to know how the less than or equal sign works. I will not ask you to justify stuff about using the comparison between numbers by starting from these axiomatic properties. I, however, want to emphasize that much of what we can say can work provided these properties hold, even if we replace the real numbers by some entirely strange foreign objects on which the ordering is defined in a very different manner. There is in fact an entire field of mathematics called order theory, which studies sets with a relation between elements that satisfies some, possibly not all, of connexity, antisymmetry, and transitivity. Properties 5 and 6 are only statable because we can do arithmetic with the numbers. Property 5 says that the order respects addition. If A is less than B, then A plus C is less than B plus C. Property 6 says that the order, if A is less than B and C is positive, then AC is still less than BC. Notice that if C were negative, then our experience tells us that the direction of inequality should be switched. I should add that up through property 5, there is no preferred direction in this ordering. If we reverse the direction of the comparison, replacing every greater than by less than and vice versa, everything from 1 through 5 still hold unchanged. Property 6, however, forces us to admit that positive numbers are different from the negative ones from the point of our ordering. The fact that the positive side is identified means that we can actually now define the absolute value function. The way to think about it is to pretend that we are extremely ignorant and only know about the basic arithmetic properties of the real or rational numbers. We then learned about how to compare two numbers, and once we learn that, we have enough knowledge to construct the absolute value function. The definition is as you may expect. It sends non-negative numbers to itself and negative numbers to their negatives. The absolute value plays a significant role in a lot of real analysis. Here, I list two very important properties of the absolute value. First, the absolute value of the product is equal to the product of absolute values. Second, which we call the triangle inequality, says that the absolute value of a sum is at most the sum of the absolute values. I will not give a proof in the lectures here, but you can find a proof in Theorem 3.5 in your textbook. I should note that as our starting point is to understand what's different between Q and R, we have not quite reached there yet. In terms of these basic properties of ordering, Q and R are still behaving the same. We will get to this in a few more lectures. One further comment on your homework. Anytime you handle inequalities between real numbers, you won't have to justify your manipulations as long as you do them correctly. As long as you have checked that a number C is positive, you won't have to separately justify that A less than B implies A times C is less than B times C. But if you have not checked that the number C is positive, then trying to say that A less than B implies AC less than ABC will be marked as a mistake. Similar things can be said about the absolute value, except for one application, that of the triangle inequality. The triangle inequality is fundamental to a lot of analysis arguments, and since it occurs so much, it is important to know that you are aware of your use of the triangle inequality. Please make sure to always point out in your homework whenever you use the triangle inequality. Now we have reached the point of this lecture, the Archimedean property for the rational numbers. There are various ways of stating this, each equivalent to others. We will pick one here as the primary one. Proposition: if Q and R are two positive rational numbers, then we can find a natural number n so that n times Q is bigger strictly than R. We begin with a proof of this proposition. First, we can write Q equal A over B and R equals C over D. Here, A, B, C, D are all naturals. This is almost a definition of rational numbers, except that we are more restrictive in the numerator. We can do this and not be forced to make A and C elements of integers because Q and R are assumed to be positive. So A and C must be positive integers, making them natural numbers. Step 2. After plugging in the expressions for Q and R into the desired conclusion, NQ is bigger than R, and performing some arithmetic, we see that it is enough that n satisfies n times AD is bigger than BC. Step 3. Since we're doing an existence proof, it suffices to give an example of n. We will set n equals twice b times c. Because a and d are natural numbers, a times d is another natural number, and thus is at least 1. This means that n times AD is at least n. If we choose n to be twice BC, then we see that n is bigger than BC, and so the desired inequality holds. Having proven the Archimedean property for the rationals, we can ask, is the Archimedean property also something possessed by the real numbers? This turns out to be a hard question that gets at the foundations of our understanding. To prove that the Archimedean property holds for the rationals, we used very specifically our knowledge of exactly what the rational numbers are. Our problem, however, has always been that we don't quite know exactly what the real numbers are. You ask, can we not just use the decimal expansion? The answer is a bit of a yes and no. That real numbers have decimal expansions, from the reductive picture again, is a consequence of our description of what real numbers are next week. So, if we use decimal expansions to justify this, we will be doing circular reasoning. In fact that 0.99999 repeated and 1 are the same number is a manifestation of the Archimedean principle. And we see here one way that decimal expansions depends on Archimedean principle at work. We conclude this lecture by showing you some consequences of the Archimedean property. I state these statements without proof. They are assigned as homework exercises. To prove them, you should aim to somehow transform each of the statements using arithmetic into exactly the same form as the Archimedean property. The first statement reads, if Q is a positive real number, rational number, then there is a natural number n such that Q is strictly bigger than 1 over n. The second statement reads, between any two distinct rational numbers, you can always find a third rational number different from either. The first statement can be interpreted as saying that infinitesimal quantities do not exist among rational numbers. The second statement can be interpreted as saying that the rational numbers are dense and have no sizable gaps between them. That's it for this week. Here are the LaTeX code for the symbols introduced in this lecture. One more time, please remember to work through the exercise sheet. On Monday, you will be discussing your work with your classmates. As the problem set, which will be published on Monday at noon, and whose first draft is due on Eli Review by Wednesday, will have questions very similar to the exercises. Spending time to work on the exercises will pay off in you being better prepared for the problem set. With that said, see you in class on Monday.